Okay, so today our big goal is to get through what's called the fundamental theorem of calculus. So before we do that, we're going to look at I call it an oh-duh theorem. It's one of these where it seems like it's going to be pretty obvious, but it's a very, very powerful tool. So consider, if you will, I have some function y equal f of x, and it's from A to B. We now know that this area, okay, we know this area can be defined using a Riemann sum. Okay, make sure you're muted, please. And we also know that we can write it as the definite integral that we introduced last day. So the area here I know is, now here's how we're going to write it. Now we don't know what it is yet. We don't know how to calculate this, but we know this is a numerical value. It's going to equal this area. Now imagine that I want to make a rectangle with the same area as this. And the rectangle is going to have the same base. Now, for example, let's suppose this width was 20 and the value of this integral, let's just say, was 100. Could I find a rectangle with width 20 that has area 100? Yeah, of course, it'd have a height of 5. That's fairly an easy notion. There's a rectangle out there. Let's say it's that one right there. Okay, let's say that this rectangle here has the same area as the area under the curve, because whatever numerical value this is, the base times height, I'm saying, is the same numerical value. Okay, this is basically the theorem. We said that's pretty easy. I have an area and I'm going to set it equal to a rectangle with the same base. That means there must be at least one place. Let's call it right here. And we're going to call that Z. There must be at least one place. Now, in my picture, there's a few, but there's at least one place where if I multiply the base times the height, I will get the exact same value as the integral. So in this picture here, we're going to say that's f of z times the width of the interval, which is b minus a. Okay? This is called the mean value theorem of integrals. Now remember, we have a mean value theorem for derivatives. That was the rolling ruler theorem, the one where the secant line is parallel to the tangent line, and you had that on the last test. This is called the mean value theorem of integrals. It's completely different. It just says, hey, look, no matter what, there's going to be a place between a and b, call it z, where if I multiply that height by that width, I'll get the same value. So that also means that I could write f of z as 1 over b minus a times the integral from a to b of f of x dx. And so the mean value theorem really is kind of stated in this form. If you have a definite integral that you can evaluate, there's a place in there, we'll call it z, such that that height is equal to 1 over the length of the base times the area. That z, this f of z, I'm sorry, we often refer to as the average value of the integral, the average value. So it's the average value of f of x over the interval from a to b. So think of it a different way. If we said, let's do what we did last day with the Riemann sum. If we were to subdivide this into a whole bunch of little rectangles, right? I'm going to subdivide this into a whole bunch of little rectangles all the way across. And I mean a lot of rectangles, like not 10, but maybe 10 bazillion. I'm going to subdivide this into a whole bunch of rectangles. If I then said, let's take the height of every one of those rectangles, just the height, and let's average all those heights. That's what this would be. This would be the average height of all of the rectangles if I could put all of them in there. So the mean value theorem just says there's a place where the height times the base equals the integral. And you say, that's kind of an oh duh. I mean, that's really not that complicated. But this result is huge. Now, it turns out, depending on the complexity of the function, finding the value of z can be really difficult. If my function was a higher degree polynomial, by the way, then finding the value of z would mean I've got to solve a high degree polynomial equation, and that would not be an easy thing. Finding the value of f of z turns out to be absolutely trivial. You see, if I know the value of the integral, then I just do this, and now I've got f of z. That height is easy. Trying to figure out the value of z would now mean I'd have to solve a complicated equation, perhaps. So rarely will you ever actually be looking for z. You're only looking for f of z. That's the easier road. Okay, so I got it. No big deal. Not that exciting. But we're going to use it a little bit later. Now, we did a problem last day where we found the area under the curve. You guys remember we did this with the parabola? Let me see if I can remember. I think the parabola was f of x is, help me out here. It was x squared. Was it x squared plus 2? No, it was 3x squared plus 2. I'm going off the top of my head. Was that what it was? This was, we did the rectangles. And
yeah, that's correct.
Okay. And when we did the problem, we expressed the problem. We didn't actually solve it. We did it using limits. Do you remember what answer we got when all was said and done?
69.
Was 69? Okay. Beautiful. So here's what I've got. I've got a picture. I want to apply the mean value theorem to this problem that we've already done. So this is a loose drawing of my picture. There's 1, there's 4. The mean value theorem says the average value, we'll call it f of z. Some people just say average value. F of z, what does f of z equal? F of z, well, what's the width of my interval? It's 4 minus 1, so it'd be 1 over 4 minus 1 times the integral, which is 69. So the mean value theorem says that the average height of this interval, now right there, that point would be the point 1, 5, and that point right there would be the point 4, so it'd be 16, 48, 50. So if I broke this up into a lot of little rectangles and then I said, let's find the height of each of those rectangles, that would be time consuming. Then the average height, that's what that means, would be 23. So if I said, what is the average value of this function over this interval? The answer is 23, because it would be 1 over 4 minus 1 times the integral. So it's that. So in my picture, if I wanted to find the z, you'd actually be solving this equation. Now, I said before, we will rarely be looking for z, because to find z means I have to have an easy equation. If this was a higher degree polynomial, this could be very difficult. But right now, because that was only a quadratic, solving this equation should be pretty easy. So that would be 3x squared equals 21. X squared is 7. X is plus or minus root 7. Oh, but in that interval, that would mean x is root 7. So my z, if you will, is root 7. Now, root 7 is somewhere between 2 and 3. So root 7 is probably somewhere in here. So here's what we're saying. If I take f of root 7, which would be 23, and I multiply it by the length of this interval, which is 3, I get the value under the curve. That's it. That's what the mean value theorem says. Okay, that picture kind of explains everything. Okay, now that we got that out of the way, because again, that's not the complicated part, but that's just a piece of a bigger puzzle. Now we're going to start the fundamental theorem of calculus. There's 2 parts to it, 2 halves. The first half is much more complicated than the second half, and the second half turns out is the one we use the most, but we can't do the second half without, well, the first half. So let me draw you a picture. This is going to be the t-axis. This is going to be the f of t axis. Normally it would be the x-axis. T is what is called a dummy variable. I could use any letter of the alphabet, but I don't want to use x. I'm saving x for something else. So I have a picture. Looks familiar, I hope. And this would be y equals f of t. Okay. Now, let's suppose there's a place anywhere between A and B I want to stop. And by the way, if I said, what's the area, the entire area, just so we know, this entire area we already know is the integral from A to B of f of t dt. I can use any letter of the alphabet. I just need these to be the same letter. Okay, we're going to use x to represent something else. I want x to be any place along here. Let's say x is right there. I want to find that area. I'm going to define this area to be little f of x. And f of x is going to equal the integral from a to x of f of t dt. Now, I know that looks kind of intimidating and scary. Well, my lower limit is a, my upper limit is x, and my function is f of t. So that should make perfect sense. But I'm going to define that to be f of x, which is, I'm sorry, my bad, sorry. Not little f, sorry, capital F. Sorry about that. It can't be the same. All right, I'm going to call it capital F of x. And I like to think of it as the area so far. So if I went from A to x, A to B, so that would mean that this quantity right here would be, based on this, if going from A to x, we're going to call capital F of x, then going from A to B would make this clearly capital F of B, based on what I'm defining this as. Okay, clearly that's what that would be. So our goal right now is to figure out what is the relationship between little f and big F. Because there's an integral in here, we're thinking somehow antiderivative derivative relationship probably would make sense. We just have to figure out how to do it. So again, this area right here, we're going to call capital F of x. Okay, that's it. So now, with that statement right there, I want to move down the road just a little bit. Let's call this x plus delta x, meaning this width right here is delta x. So if I want the area from here to here, that would be f of x plus delta x. Because remember, what we're going to put here is just the furthest to the right. The way we've defined this, we're starting at A and we're moving to the right to whatever this value is. A to x, that's f of x. So A to x plus delta x would be this guy, and I'm going to write it like this. Okay, again, that just goes back to based on this definition. Okay, by the way, if you have a question, go ahead and
Ask it now.
Respectfully blurt it out, because I haven't actually done anything. I'm just defining functions. So it's not a question of why. You can't ask why on the definition. This is the definition of it. That's it.
I wasn't
why,
asking for a
that's what it is.
definition.
What's that?
I wasn't asking for a definition. What I was thinking is, since you have a and x, wouldn't since a to the x is the domain of where you're evaluating the function at, could you do domain of a to x, then the domain of x to b, both of those added together is equal to the whole a to b function.
Yeah, I could say this plus this is this, yes, but that's not where we're going.
Is that applicable for anything that we're going to be doing?
Yeah, that's automatically true. We proved that last day. So that's Nate's question is, if I took this and I added it to this, do I get this? Yes, that's absolutely always true.
Is there any way we can use that?
No.
Okay, that's all.
We got a to x, and now I have a to x plus delta x. Boom. I would like that area right there. How do I find that area right there? Now, this is really, really simple. And I always like to go back to simple examples. If you were in an algebra class and I have a circle of a certain radius, and then inside I put another circle of a different radius, and I want you to find the area between the circles, you go, man, that's so complicated. I'd have to set up a grid. I'd have to find all these complicated things. And then there'd be one smart kid in the class who would say, well, why don't you just take the big area and subtract the little area? And everyone else would say, oh, yeah, didn't think of that. I have a rectangle, and here I have a rectangle, and I'm going to tell you all the different dimensions, and I want the area between them, and you're going to, let me find that area and that area. And that. How about just the big one minus the little one? I mean, that to me, that's the ultimate no-brainer. So I want to find the area. I want to find the area right here. Don't we already have a way of describing the big area and a way of describing the smaller area? So wouldn't the area right here simply be the difference, everyone? Do you agree with that? I don't have to be clever. I don't have to set up an integral. This right here is this area. This right here is this area, and I want the area between them. So this minus this. So the area I'm looking for is simply f of x plus delta x minus f of x. Now, because of the way we're defining our area so far function, we're defining it based on the left end point and where I'm ending. Let's start with this. Now, this is this integral here minus this integral here. Now, I'd sure love to write this as one integral. That would be really useful if I could write this as one integral. Well, let's see. I want to put a plus sign here. Based on last day's lecture, I want to put a plus sign here. What do I do with these limits? Anybody?
Flip them.
You swap it.
Yep. Now, why is that cool? Because we showed last day when you're adding two integrals and you start and end at the same place, this goes from, so think of this goes from x to a, and then this goes from a to this. Can I now write one integral that goes from x to this? Yes, that's the whole point. So I can now write, oh, I'll put it, I'm running out of room here. This is the integral from x to x plus delta x, which makes sense, of f of t dt. Great. It's not the value, it's this relationship. So now what I'm going to do, sorry about it, I'm gonna erase this stuff up here because I need the space. But we already have this now. Okay. I now have this difference is equal to this. Now, according to the mean value theorem, according to the mean value theorem, there's got to be a place in here, let's call it Z, such that, right, the rectangle f of z multiplied by delta x has to equal this area, right? That's what the mean value theorem was. That's why we did that first. There is a z in there that's between x and x plus delta x. I'll write it like this. I know that, and here's what I also know. I know that f of z times the width of the interval. Before we said, you know, b minus a, that was generic. The width of this interval is delta x. That's times delta x. And that's got to equal what? This. Okay, but what else does this equal? This also equals this. Okay. So what if I want f of z by itself? Then I'd get 1 over delta x. Delta x is not 0, but obviously when you see a delta x, you know there's a limit coming somewhere. Okay, I know that is true. But what else does that equal? That equals this over delta x. Because I know that this equaled the numerator, so that, you know, does that have a familiar look to anybody?
Difference formula or whatever you call it.
Keep going.
Definition of a limit. Definition of a
That
limit.
kind of looks like the definition of the
The
derivative.
limit.
Well, the limit of that.
Sorry,
Does
yes.
everyone think that kind of looks like definition of a derivative? It's missing a limit, but isn't that definition of the derivatives f of x plus delta x minus f of x all over delta x? That looks a lot like, now I need a limit, but right now f of z, this height is exactly equal to this statement here. So what if we took a limit? Well, let's see. do you all agree with the following statement? That f prime of x, this is capital F, is equal to the limit as delta x goes to 0. Because when we said, hey, this kind of looks like the definition of the derivative, well, as soon as I throw a limit in there, it is the definition of the derivative. So f prime of x is this limit. But that means it's also the limit as delta x goes to 0 of f of z. That guy's kind of interesting. That guy's really interesting. I have no problem with this. This is pretty straightforward. Heck, this was true without anything I've written before it. That's the definition. This is the guy I want to look at, though. Now, it's the most important part of proving the fundamental theorem of calculus involves Star Wars. Okay, now I want you to think back, and I'm not joking, by the way. This is how I prove the fundamental theorem. Think back to the original Star Wars movie. Okay, I'm not giving any spoiler alerts. That came out in 1977. So if you haven't seen it, that's, you remember the garbage pit scene when Luke and the gang, and they're in the garbage pit of the destroyer, big Star Destroyer. And what happens? The walls start closing in. Okay, everybody remembers that scene? What George Lucas was trying to tell us, and by the way, a lot of people don't realize how much calculus you see in your movies and things like that. George Lucas was trying to demonstrate how they proved the fundamental theorem of calculus, in outer space. I think that's what it is. So here's where you are. There's the wall. The other wall is at x plus delta x. And that wall starts closing in because delta x is approaching 0. Okay, so that's what's happening. The first wall is not moving. Delta x is approaching 0. So the second wall here is closing in. Z is a value between x and delta x. Okay, so think of Z as, Luke Skywalker, and he's in the garbage pit. But if that wall keeps coming and keeps coming and keeps coming, and poor Luke is in between, what's going to happen eventually? Luke is going to become one with the wall. Do you all agree with that? Does everybody see what I mean? It doesn't matter. There's something in between the walls, but as this wall becomes this wall, the thing in between is also going to become this wall. So as delta x approaches 0, what's happening to Z? Isn't f of z becoming f of x? Because it just got squished into the wall. Tell me if you can see that. Okay, I have something between the walls, but the distance between the walls is approaching 0, which means anything between the walls will become part of.
So that means z is equal to 0 then?
No, that wouldn't make any sense whatsoever. Z is right here. Delta x is approaching 0, which means that everything is turning into
X.
So this is, the limit is little f of x. Okay, what does that mean? Capital F prime of x is equal to little f of x. Our goal was to figure out the relationship between capital F and little f. It turns out little f is simply the derivative of capital F, which would mean that capital F must be the antiderivative of little f, which makes sense because we define capital F as an integral. So now I'm going to erase this and then restate what we just showed. We have just looked at the first half of the fundamental theorem, and basically the first half of the fundamental theorem can be summarized like this. Okay, if f of x equals a to little x of f of t dt, then f prime of x, which would be d dx of this, if f of x equals this, that's how we started this problem, then the derivative would be d dx of this, and that's little f of x. That's what we have just proved. Okay, so let's do an example of this. You notice there's no integration taking place right now. There's only a derivative. We haven't actually integrated anything. We said the relationship is if capital F is defined by this integral, which we called the area so far, then f prime of x we just proved is little f of x. That's why, remember, we started with f of t. I said t is a dummy variable. We could have used any letter of the alphabet. I didn't want to use x. I wanted x to be a variable on the horizontal axis that represented any value between a and b. So let's do an example. I would like you to find the derivative with respect to x of the integral from 3 to x of the inverse tangent of t cubed. Okay, that's pretty horrific. That's absolutely terrifying. Anybody want to tell me the answer? It would be inverse tangent of x cubed. That's pretty easy. If it's a to x of f of t dt, then the answer says f of x. Oh, that was actually really simple. Well, because I took the derivative of the integral. If derivatives and integrals undo each other in a sense, I just took the derivative of the integral, which in a sense undid each other, but my limit of integration involved the x itself. We didn't actually integrate anything. That's the nice thing. Now, this is the easier path. There's a more complicated version. What if that's not an x, but a function of x? Ooh, is there a chain rule to this? Yeah, and that's the one I want to show you. That's the one, by the way, that most textbooks leave out, which is unfortunate, you know, because we kind of need it. Well, if this is the definition of f of x, then what if I have f of u of x? Then wouldn't that be a to u of x? Everybody see that? So assume this is a function and not just x. Now, if I want to do the derivative of the left side, d dx of f of u of x, well, I know that's f prime of u of x, and then there must be a chain rule factor times du dx. Oh, but f prime of u of x, according to this, f prime of u of x should just be little f of u of x. F prime of x is little f of x. So f prime of u of x should be little f of u of x times the chain rule factor. And that's the most general case. Okay, I want us to know this case. So if I'm doing this on something that's a little more complicated, we'll do one more example. This type of problem does not come up much in calculus 1, 2, and 3. This type of problem typically comes up in upper level math classes, and it's actually a fairly common problem. And then when the students see it, they can't remember that they learned it in Calc 1. I would like you to find the derivative of the integral from -2 to x cubed of the square root of 5 plus e to the t. All right, just something horrible. This can't be integrated, and it's not even important because I'm doing the derivative of this. So we're going to use this. Well, right off the bat, I know that all I need to do is replace t with this. I know I got to do that. So my answer is going to be 5 plus e to the x cubed. But because that's not an x, we saw that there must also be a chain rule factor. So what else must I include in this answer? Anyone?
The derivative of 3x.
Of x cubed.
My bad, yeah, x cubed.
And that's it. That's the only additional step I need to do. Everybody likes this because it's so cool. The derivative of the antiderivative is essentially the original function, except that I've got to insert whatever the variable is. So my final answer ends up being a function of x, ultimately, not a function of t. Now, that part right there is the more complicated proof, but it's actually the lesser important. But now this allows us to do the second half. And the second half, it's easier for me to show, but it's actually far more important. Now, let's take something we already know about antiderivatives. Let's take something really simple. If I asked you to integrate 3x squared dx, what is the antiderivative of this?
X cubed.
X cubed. Is that
Plus
it?
c.
Plus c.
Plus c.
Why plus c? Let understand, why do I have to put the plus c? Would it be true if I left out the plus c? Actually, it wouldn't be true if I left out the plus c, because right now every constant that exists could be an antiderivative. If I gave you an initial condition, like, f of 3 equals 11, so I gave you some initial condition, then you could find the specific value of c. But if I don't put the plus c in there, it would only be true then if plus c was 0, and plus c is probably not going to be 0 very often. So I have the plus c because I want to consider every conceivable antiderivative. Oh, so if I said, consider that g of x and f of x are antiderivatives, of 3x squared. Both g and f are antiderivatives. So Nate found an antiderivative, and he wants to add a +5, and William found one, and he wants to do -7. You're both right. But how do f and g differ? Would g of x equal f of x in general? They're both antiderivatives. I just said, well, Nate had x squared plus 5, and William had, x cubed plus 5, and William had x cubed -7, and they've both given correct antiderivatives. Do they have the same answer? Did they both just give the exact same answer? No. How do their answers differ? By
the c value.
By a constant. Oh, so in general, would that be a true statement? If f and g are both antiderivatives, then they're equal except for a constant. In other words, they only differ by a constant. So of the infinitely many antiderivatives you could tell me for 3x squared, every antiderivative you could possibly come up with, they only differ by a constant. They don't differ by another function. They don't differ by an x or a cosine x or an e to the x. They only differ by the constant at the end. So there are infinitely many correct antiderivatives, and all of them differ by a constant. That's hugely important that we understand that statement. Okay, so that's why we always throw the plus constant at the end, because without more information, like an initial condition, I don't know what the constant is. So I just throw it in there. So now let's consider, all right, let's take what we now know. So I've got this guy here. That's how we started it. Now I want you to suppose that g of x is also something to do with this. Remember, this says here that f prime of x equals little f of x. That's what we proved earlier. Let's suppose, and by the way, and another way of thinking about that would mean then that capital F of x is an antiderivative of little f of x. That's what you can assume. So let's suppose that g of x is also a solution of this. Because g prime of x is also equal to little f of x. Does that mean capital F and capital G are equal? No, that means they differ by at most a constant. Okay, you with me so far? If they differ by at most a constant, then we can say, I'll write it in reverse. I'll say capital F of x must equal g of x plus a c. The c could be 0, but to require c to be 0 is dangerous. If every real number of c is a possibility, then leave it as plus c, right? Don't put a specific one in without prior information. Now, with that said, going back to this statement, what is f of a? F of a would be the integral from a to a of f of t dt. And what's f of, which by the way, sorry, I need to erase this. That would also be g of a plus c, based on what we just said, because we said f and g differ by a constant. What's f of b? That'd be the integral from a to b of f of t dt, which would be g of b plus constant. G of a would be a scalar. G of b would be a scalar, right? G of x is a function. Okay, so far so good. Well, this is a scalar. So here's something I want you to understand. We call t a dummy variable. Just for fun, if I wrote the following statement, f of, I don't know, q. Are these the same thing? Please mute yourself. I hear all this outside noise. Does this say the exact same thing?
Yes.
Yes, because it's a scalar. If I said f of x, is that the same as f of q? No, no, no. I'm using those as variables. But this is a definite integral. This is a scalar. So the letter of the alphabet doesn't affect the numerical value. Okay, again, I want you to think simple. If I said f of x is x squared, find f of 3, you'd say that's 9. If I said f of t is t squared, find f of 3, isn't it still 9? Because I used a different letter of the alphabet, but I still calculated it at the same number. That's a function, that's a scalar. Oh, okay, so it didn't matter what letter I was using once I evaluated. That's the part I want you to see. So would it be correct to then say, going back to this statement right here, look at this. Look at this. F of B minus f of A is equal to this, excuse me, this minus this. Huh. So the fact that they differed by a constant didn't matter when I did this. And in each case, that's the integral from A to B of f of t dt. This is a scalar. And here's where a lot of the textbooks just sort of wave their hands and say, and therefore, no, any letter of the alphabet I put here, it would still be true. So now, so what did we just say? Remember, what's the relationship between capital F and little f? The derivative of capital F is little f. So the antiderivative of little f is capital F. We know that. Okay, that's not even a question anymore. We already know, and in fact, I've written this already, the antiderivative of little f is capital F plus c. We know that because the derivative of this was this. I want you to stare at what we have now. I give you a function, little f of x. Capital F is its antiderivative. But this says I took the antiderivative and I evaluated it at this number, and then I evaluated it at this number, and then I took the difference. That's it. I took the antiderivative of little f and evaluated at these two endpoints and took the difference. That's it. No rectangles, no summations necessary. So, but that's actually really simple. We're going to do some examples. This statement right here is often considered the single most important, certainly STEM thing in, well, human history. The ability to evaluate a definite integral is actually this easy based on all of the stuff we just did. And the key was, because all antiderivatives can only differ by a constant, do you notice I don't have a plus c in my answer? I don't need a plus c. Why don't I need a plus c? Because I would have this plus c minus this plus c, and every value of plus c will do what? Cancel. So here's a very powerful statement I'm going to make, and you only get to do this one other time. In differential equations, you get to do this. Every antiderivative, every possible plus c you could come up with when you're doing an integration, when you're doing a definite integral, every possible plus c you could come up with is going to end up canceling because it's on both sides. Since every value of plus c will give you the same numerical value in your definite integral, you actually can choose the plus c you want. There's one problem in differential equations where this also comes up. And so therefore, what value of c will you choose in your definite integral? Anybody?
A zillion.
How about 0? If every plus c will give you the same definite integral, then choose your plus c to be 0. So you don't actually have a plus c in a definite integral because it would have always canceled. One of the few areas in mathematics you get to choose the constant. That seems kind of weird, but it's because we just proved all antiderivatives differ by a constant. But this was this plus c minus this plus c, and the c's had already canceled. So let's go back. Oh, I don't know. Let's do that problem. 3x squared plus 2. This took us a long time last day. We had to create rectangles, we had to set up the areas, then we took limits and we did the summations. Remember, that was a really long problem. Okay, but we all got through it. Here's what I'm telling you. Let's find the antiderivative of this first. So what's the antiderivative of that function? Anyone?
X cubed plus C.
Plus, what about that guy?
X.
How about plus 2x? Now I said we don't technically have to put the plus c because we can choose our plus c, and I'm just going to pick a plus c of 0. Now that's my antiderivative. So how do I go from here to here? The notation we generally use is bracket or vertical bar, and then we write the numbers in the same order. And I'm going to show you what the notation means, because the notation isn't exclusive to this. This is actually universal math notation, but in this context, it's very specific. There's my antiderivative, and it says I'm going to evaluate my antiderivative at both of these endpoints. Okay, well, let's see. If I evaluate at 4, what would I get? I get 64 plus 8 minus. Now I'm going to evaluate it at 1, and I'm going to get 1 plus 2. So that would be what? 72 minus 3. Oh my gosh. I don't know about you, but I think this was a little easier than what we did last day. Do you agree? A little bit easier. Yeah, got the same answer, of course, because that's the answer. Now, the notation, when it comes to calculus, everybody hates notation. But the problem is, if my notation is imperfect in any way, it will be misinterpreted because I've actually written something else. So I'm going to go back to baby algebra for a moment. I'm going to show you different forms of notation because this is what we're actually doing. So in baby algebra, let's suppose I defined f of x to equal x squared, and I say I want you to evaluate f of x at x equal 3. Well, most of us would just say f of 3. You're right. But the formal way of writing this, believe it or not, would be this: f of x vertical bar x equal 3. Now you have seen this before when we did related rates. Remember? Oh, I had my answer and then I want to evaluate it at something. Whenever you have a vertical bar followed by something of this form, this means evaluated at. That's what this means. So in this case here, what I'm really saying is, think of my antiderivative evaluated at x equal 1 and evaluated at x equal 4. Oh, I'm going to do it twice. And when you do it twice, you always do the top one minus the bottom one. If I was only doing it once, then that's my only answer. So if I said I want you to find, f of 3 and I want you to subtract f of 1, then I would have put x equal 1 here and an x equal 3 here. So when there's two values, you put top one minus bottom one. If there's only one evaluation, then you just put it at the bottom. This is universal math notation. This isn't calculus. I use this notation in remedial algebra so that students get used to how do you ask the question. Because sometimes you might say, I'm going to have a function. I want you to evaluate it at this ordered pair. Ah, okay. So, I could put an ordered pair here. So in this case here, that's all we got. Now, understand the relationship between the integral and the picture. The integral right now, our basic definition of the integral is it's the area under the curve of y equal f of x from a to b. That's the picture we've been using the last 2 days. There's far more application than just area. Area is the lowest level application. When we first learned derivative, right, our most basic definition was it was the slope of the tangent line at a particular value. And then we realized, oh, okay, it's way bigger than that. It's an instantaneous rate of change. There doesn't have to be a graph. There doesn't have to be a tangent line. It's just the rate of change at that moment. We used it for related rates, right? We don't need a picture to do a derivative. That was just our introduction. Our introduction to integration is area under a curve. But it doesn't have to be just that. It could be way beyond that. So let's consider f of x is the sine function, and I am interested in one hump of the sine wave, okay? So I know what a sine wave looks like. So a sine wave looks like this, but I only want to go from here to here. I'd like the area under the curve. Okay, area under the curve. So I want this area between the curve and the axis. Well, that means I want the integral from 0 to pi. Again, lower limit to upper limit. The order does matter. If I swap the order, we already know that changes the sign of the answer. And that's not good. Of sine of x dx. Now, if I was to do this using rectangles, this is very interesting. I just want you to see something. Let's suppose that we were going to write the Riemann sum. We said, well, let's break it up into a whole bunch of rectangles, right? Well, first of all, because it's a sine wave, I think we agree that every single height, every one of these heights would be irrational because I have the sine of an angle. And what about my widths? I'm subdividing pi. All of my rectangles would have irrational widths. All of my heights would be irrational numbers. And then I would find all of those areas, I'd add them up, I'd take a limit. Clearly, that would represent a very, very ugly answer. I think we all agree. But I'm not going to do it this way. I'm just going to calculate it directly because it's easier and it's correct. So if I calculate this, well, first of all, what's the antiderivative of the sine function?
Cosine.
Cosine?
Oh, yeah, right. Negative cosine.
Negative cosine, good. The derivative of sine is cosine, but the derivative of negative cosine gets me back to sine. Now, whether you write vertical bar or you write brackets isn't the issue. Often you might have multiple terms, so you would bracket them off. And so if there's no way it can be misinterpreted, it is absolutely correct to go like this. This is absolutely correct. But if I have stuff, in other words, I've got to bracket it on both sides, the danger of using vertical bars, if I have to enclose it, it looks like absolute value when I do that. So that's one of the reasons I want you to understand that using a bracket or using a bar, it's exactly the same thing. There is no difference mathematically between these two statements. So a lot of folks will say, you know what, I'm just going to always use the bracket because then when I have to enclose it, I don't have to change my notation. You can't enclose it with vertical bars because that now means absolute value. And there's no absolute value in an antiderivative. So I get what? The negative cosine of pi minus the negative cosine of 0. Cosine of pi is -1? Huh. That's interesting. I have an interval that goes from 0 to pi of a transcendental function. Every one of these heights would be irrational. And after all that, my area is exactly 2. You didn't see that one coming. Everything about this problem has irrational written all over it, yet my area was simply 2. Cool. Now, what if? And I mentioned this last day. Some of you had asked the question. And I think, Nate, you were one of the ones that we were talking about this. What if I said, let's go all the way to 2 pi? The statement is, quote unquote, this is the area under the curve. Area under the curve. But now I'm going to go to 2 pi. Well, in my picture, I know that the sine function has some symmetry going on here, that this region here and this region here should be identical. It just got flipped over. So if I said area under the curve, well, let's see, this would be negative cos x from 0 to 2 pi, which is, okay, cosine of 2 pi is 1. So this would be -1 minus cosine of 0 is 1. Wait a minute. Why did I get 0? If this area here was 2, shouldn't I have gotten 4? No. Because this curve dipped below the x-axis. The area, quote unquote, under the curve, all of this, therefore, produced a negative value. Oh. So when you're actually calculating an integral, the value of an integral can be 0. The value of an integral can be negative. If I said do the integral from pi to 2 pi of the sine function, you would have gotten a negative value. Okay, so yeah, an integral can be any real number. If I'm asking you to actually calculate an area, that means you actually have to set up the problem in such a way. Okay, so if I actually wanted the area bounded by the curve and the axis, then I would have actually had to make a separate problem because now the curve's underneath. That's a different problem altogether. So I don't want you to worry about that. That's next week. We look at that problem. So for right now, when evaluating a definite integral, you just find an antiderivative and plug in the limits of integration. That's it. That's what the fundamental theorem of calculus was all about. It got us to that result. And that result is so easy to use once I know how to integrate in general. Okay. The only tricky thing remaining, by the way, the only tricky thing remaining is if I have substitution going on. And that's the next couple of days we're going to look at that problem. So let's suppose we're just going to do a simple antiderivative. I want to do the antiderivative from -1 to 2 of, let's keep it fairly simple, of 2x squared minus 3x plus 4 dx. I want to keep this really simple to show you that even simple problems can be really, really messy. Let me grab my calculator here too. Okay. So I want the answer to this. So I do not break this up into 3 integrals and rewrite it. Some people are doing that. It's very, very inefficient. No, just we integrate one term at a time. So what would the first one be? Anybody?
2/3 x cubed.
2/3 x cubed. See, I always do the exponent first. So then this would be minus
3/2.
3/2. And then the last one,
4x.
4x. I'm going to evaluate that from -1 to 2. So what I do is I put the 2 in for all 3. And by the way, whether you do this by hand or on your calculator, however you do it, just don't make arithmetic mistakes. So when I put that in, 8 times 2/3, so that's 16/3. 4 times -3/2, so that's -6, plus 8. I put in the -1. So -1, when I cube it's -1, so that'd be -2/3. 1, so -3/2. -1, so -4. All right. Don't sit there and spend a few minutes doing common denominators and all that. Just use your calculator and use the fraction key. So that's what I'm going to do. So fraction 16/3. The fraction key is one of the great inventions, that in the dishwasher, because I hate washing dishes, by the way. Now I'm going to enter that. -2/3 minus 3/2 minus 4. And I get 27/2 on my calculator. I don't want a decimal. I want the answer. So, well, can't I give a decimal? Yeah, but unless it's a terminating decimal, there's no time in human history where you would ever take a fraction and round it off as a decimal. That does no. If my answer is thirds, I don't want to see any 0.3s. I just want to see thirds. That's the answer. That's a simple answer. Use your calculator. Now, what does this mean? Well, if it was area, that means that's the area under the curve between -1 and 2. But it doesn't have to have an application right now. When we just practiced doing derivatives after a while, you didn't draw pictures. You just took derivatives. Right? You get used to just doing that. So right now we want to just get used to evaluating definite integrals because this is not a complicated process. Okay. Let's do another. And I'm going to show you some really nice shortcuts. There are certain shortcuts that exist. And again, shortcuts are not emphasized because we want to learn how to do something. And I always maintain a shortcut is meaningless if you don't already know how to do a process. You see, I'm going to have a party this weekend at my house, and I'm going to give everybody the shortcut to my house. And everybody's going to get utterly lost. Why would everybody get utterly lost if I give you the shortcut?
You don't know the way there.
Because you don't know the way there. It's like, if you knew the way to my house, now the shortcut is relevant and you can use that. But if you don't know how to get to my house and I give you the shortcut, you're all going to get lost and end up in another country or something. Probably Mexico, not Canada, I guess, because closer. People sometimes forget that. A shortcut doesn't mean anything if you don't already know how to do something, because you don't know what processes you're shortcutting. Okay. So I'm going to show you a really cool one. So first of all, I'm going to define something. This is something you learned maybe in algebra and in pre-calculus, but hopefully at least in pre-calculus. First of all, the concept of something called an even function. Now, the definition of an even function is that f of negative x equals f of x. Graphically speaking, an even function, what makes something an even function graphically is that you have what's called y-axis symmetry. The y-axis acts as a mirror. This is called reflection symmetry. It's sometimes called line symmetry, axis symmetry. There's two types of two-dimensional symmetries we look at typically. Reflection, mirror, line symmetry. That's all the same thing. The other would be some form of rotational symmetry. So an even function is anything, you see, if that point right there were x comma f of x, then this point, this mirror point over here is negative x comma same y value. In other words, when I inserted x and negative x, I got the same y value. That's what this means. Now, an example of an even function would be any polynomial of even degree. Oh, so for example, if I said, consider f of x is 3x to the fourth minus 2x squared plus 8. That is a function of even degree because each term, and 8 would be of degree 0, which is even. Okay, every term in that would be even degree. So let's check. If I wanted to do f of negative x, then that would be 3 times negative x to the fourth minus 2 times negative x squared plus 8. And that would be, let's see, a negative to the fourth power, that's 3x squared. That would be minus 2, fourth power, that'd be minus 2x squared. And that is my original f of x. See, it worked. If I have a function where every term's even degree, are there any trig functions that are even functions? Anybody know? Do any trig functions, in other words, have
Cosine?
Cosine function.
Good. That's the most important, maybe of all the even functions we work with, is the cosine function. Cosine function, oh yeah, cosine goes like this, right? It's a mirror at the y-axis, and so is the secant function because it's the reciprocal. Even functions are hard to come by, and here's why we love even functions. I'll show you why. All right. Consider. All right, let me just. I want to keep the graph simple. Oops. The term we use here are the limits are symmetric, or I have an integral with symmetric limits. Symmetric limits would mean I'm going from -1 to 1, -5 to 5, -10 to 10, okay, -a to a. That's what we call symmetric limits. If I have an even function with symmetric limits, because of this, of the fact that it's an even function and my limits are symmetric, is it safe to say that the area of this region should equal the area of this region? Do you think that's true or false?
True.
True.
Absolutely true. In other words, this region would be congruent to this region. Why? Because I'm going the same number. If I went -3 to 7, no, that's right. I have to -3 to 3, -7 to 7. If I have symmetric limits and an even function, then the following statement is absolutely always true. 0 to a times 2. And I will guarantee you, every problem that exists, I looked at all of them last night, just every problem that exists. If you have an even function with symmetric limits, it is always easier to do this, without exception, every time. And here's part of the reason. The antiderivative of an even function, we haven't defined odd yet, but we will in a moment. An antiderivative of an even function is odd, and the antiderivative of an odd function is even. So your life will always be easier doing this, always. Okay, we'll do some examples in a moment. Now I want to define odd function. An odd function is one such that f of -x is the negative of f of x. And graphically, And again, very, very powerful form of symmetry here. An odd function, first of all, has to pass through the origin. Okay. Why? Because f of 0 has to be 0. Oh, otherwise this wouldn't work. But not only that, it has what's called rotational symmetry. If I take my graph, I put my finger on the origin and then I spin it 180 degrees, it should look exactly the same. So the two types of symmetry that we typically look at in 2 dimensions, again, is reflection and rotational. Reflection symmetry is sometimes called line symmetry. It means you have an axis that acts as a mirror. If you think about it, all parabolas have an axis that acts like a mirror, but that axis isn't always the y-axis. So therefore, parabolas aren't always even functions. But if a parabola had its vertex on the y-axis, then it would be an even function because the axis would act as the mirror. So an odd function has this behavior. So what sort of things are odd functions? Well, certainly polynomials of odd degree. So let's start with a polynomial of odd degree. So I've got, how about 3x to the 5th minus 2x cubed plus 7x. Each of these exponents is odd. Okay, a constant is of even degree, so that wouldn't work here. So now if I do f of negative x, okay, well, negative to an odd power, that'd be negative 3x to the 5th. Negative to an odd power times a negative, so that'd be plus 2x cubed minus 7x. If I factor out the negative, and I do believe this is exactly the negative of my original f of x. So that's what an odd function, you have that sort of behavior. Now, are there any trig functions that are odd functions?
All of them except the cosine and secant.
All of them except the cosine secant. That's absolutely correct. Turns out all trig functions are either odd or even. So let's take the simplest one of all, the sine function. Oh, yeah. How about the tangent function? Well, the one that goes through the origin certainly is. Okay. And by the way, if I keep going, so all trig functions other than cosine and secant are odd functions. Now, odd functions we don't deal with as often, strangely enough, as even functions in a calculus sense, but we still love them when they show up. Now, think of the degree aspects. If an even function, think polynomial, every term has even degree, then isn't the antiderivative automatically going to be odd because I've just added 1 to each degree? And same thing with an odd function. When I add 1 to each degree, it becomes even. So the antiderivatives of evens and odds are evens and odds. And same thing, by the way, with the derivatives of evens and odds. But derivatives of evens and odds, there's no shortcut. Only the antiderivatives do we need a shortcut. So now f is odd, okay? And I want to do the integral from negative a to a of f of x dx. And f is an odd function. Because when I rotate it, it looks exactly the same. It's not a mirror. No, but this, if I spin this, this region here is exactly the same. When I flip this back up, these regions are congruent. Okay. But since we're saying quote unquote area under the curve, won't this give me a negative value? Now think of the sine wave we just did a little while ago. What should the answer to this be?
0.
0. This is one we really like. An odd function with symmetric limits is equal to 0, period. You don't have to do any work whatsoever. But again, it's the symmetric limits. If my limits aren't symmetric, then there's no trick. Okay, you with me so far? So I have an integration problem and I recognize that I have symmetric limits. First thing I want to do is say, hey, is my function either odd or even? Because if it is, I can save some time, tremendous amount of time. There's no guarantee. Now, what if you have symmetric limits and you're neither even nor odd? Well, there's not a whole lot you can do in that case. Or you have an even and odd function, but you don't have symmetric limits. You see, so let's do a couple of examples of these. So I have the integral from, how about -2 to 2 of 4x squared plus 6. Okay. You never have to use symmetry. You never have to, but you always should. And I'm going to walk you through why. Let's suppose I'm not paying attention. I'm doing math while watching the Laker game, and I just didn't even notice that's an even function. Okay. So now I'm saying, okay, it's 4/3 x cubed plus 6x, and I'm evaluating from -2 to 2. That's absolutely correct. So I have 8 times 4/3 plus 12 minus. Now, here's one of the drawbacks. When I integrate an even function, I get an odd function. But when I evaluate an odd function at a negative number, that's when it can get kind of tricky, because now I'm raising a negative to an odd power, which means I got to really pay attention to the signs. I easily can make sign errors when evaluating negatives at odd functions, because I have to be more careful. So -2 when I cube it is -8. And then -8 times 4/3 would be -32/3. And then -2 here would be -12. So now let's see, that would be 98/3, and I'm subtracting, and then this would be -98/3. Right, so now I just have 196/3. Everything I did was true, everything I did was correct. But I think we agreed that this would have been easier had I just done this. And here's why I always do this, without exception. If the antiderivative of an even function is odd, by the way, this is absolutely correct. This is what most people are going to do. Look at how many steps we just took. Okay. So now I will use the brackets because I have the 2. My lower limit is 0. All odd functions evaluated at 0 equal 0. There is no exception. So when I take my even function and I go 0 to upper limit, I don't technically even have to bother evaluating at 0, because the result has to be 0 absolutely always. So in other words, I'm done. That's it. There was no other work. I have a calculator in hand. This won't be tough. I don't have a second term because I'm evaluating an odd function at 0. So the great benefit from doing this is you just eliminated not only at least half the work, you eliminated the half that might cause problems, because I'm evaluating the other half at negative numbers. So I eliminated the part that would give me the most trouble. Much easier problem. But you took a step to do this. And I eliminated several others. No, it's always faster to do this if you recognize it. Okay. So now I'm going to show you a little trick. And odd and even, all textbooks have odd and even. They do an explanation. And I'm just curious, how many of you did odd and even functions? Anybody in other classes? I'm just curious. Did anybody do odd and even functions in pre-calc? Did you spend a lot of time, or just basically, here's what they are, let's move on?
A lot of time.
That's good, because they're ridiculously beneficial if I know them. Okay. If I have odd and even functions and I know, whoops, sorry, hit the wrong button. Let me get my video back on. Sorry about that. This computer sometimes okay, I hit the same thing like 25 times in a row before we'll actually do something. So I'm going to show you a one. Okay, I pride myself in being the laziest person you will ever meet. Okay, I'm serious. I'm the laziest person you'll ever meet. Now, if you followed me around for a day, you'd find that really strange. Because while I'm sitting at my computer writing and grading perhaps, and I have a hockey game on in the TV in the other room, I might be doing crunches in between, and I have a full gym in my garage that I'm working out while I'm making a 5-course meal and doing laundry upstairs. This, by the way, this is every day of my life. I do all of these things simultaneously because I'm so ridiculously lazy. I know that sounds like a contradiction. I value my free time. I waste no time because I'm lazy. I like having free time. So when I'm doing mathematics, if the question is here and the answer is here, I want to do that. I don't want to do this. And a lot of us do mathematics with lots of sideways motions. If you can get an answer in 2 steps, don't take 10. Do it in 2. Skipping a step or doing it in your head, that's not what I'm talking about. I'm saying steps that don't need to be done at all should be ignored. So I just showed you how you could do a problem much faster. So what if we have something like this? I've got the integral from, let's say, I don't want it to be too complicated. Let's say negative 3 to 3 of 9x to the 7th minus, I don't want this to be too terrible, 5x to the 4th plus 11x cubed plus 3x squared plus 9x. There we go. All right. This one just looks terrible. But I want you to do this problem here. It's like, oh man. Now, can I use those tricks? Is this odd? Anybody, is this odd?
I feel like it is with this x to the 7th.
Yeah, but those guys, is it even? An odd function and an even function are special. If I just said, I want you just without thinking about it, write down 100 functions on a piece of paper. One of them might be odd, one of them might be even, probably not very many, because a function isn't odd or even in general. Those are very, very special functions. This function, this whole raw function is neither odd nor even. All of my exponents are not even, all of my exponents are not odd. So polynomials in general are neither odd nor even. So I can't use any of those symmetry tricks, can I? Or can I? Remember, think lazy. If I integrate this correctly, I'm going to have 9/8 x to the 8th minus x to the 5th plus 11/4 x to the 4th plus x cubed plus 9/2 x squared. And I'm going to go from -3 to 3. Oh, that's going to be ugly and messy and lots of fractions. But I have a calculator, but this is going to take me a little while. And I will do it correctly, but it's going to take me a little while. And there's a lot of calculating, a lot of steps, and a lot of yucky fractions. Didn't we prove last day for definite integrals and indefinite? Isn't the integral of the sum of the integrals? Don't we know that? So when we're integrating, weren't we integrating one term at a time anyway? So would there be anything wrong This is one you won't see in any textbook. You probably won't even see in another calculus class. First of all, yes or no? Is this true or false?
True.
True.
It's true because I took all the same terms. I said the integral of the sum is the sum of the integrals, and addition is commutative and associative. Why would I want to do such a thing? Well, because that's 0. Why is that 0? Odd function, symmetric limits. You like that so far? This is what I would do. I just eliminated most of the work in the problem. Oh, by the way, even function, symmetric limits. Oh, sorry, put the 2 in front. Try that one more time. So that would be negative 243 plus 27. So it's at negative 432. Hey, that's not ugly and it's not fraction, and then actually was kind of easy. If I just integrate this as is, like I'm supposed to, it's a long process and a lot of calculations and very messy. You have a calculator, so you're probably going to do it right, but it's not going to be short and sweet. but I had a function that had even and odd terms in it. I can always break it up. Now, here's what the giveaway is. In general, you do not break up integrals into even and odd. No, that doesn't make any sense. I broke it up into even and odd because I had symmetric limits. That's the only reason. If my limits had not been symmetric, there would be no advantage whatsoever to breaking it up. But because I recognized that I had symmetric limits, I said, hey, let me separate the odd and even, then the odd part's automatically 0. And the even part is much shorter and much simpler. You can always do this in this kind of scenario. Okay, so I just wanted to throw that out there because, again, that's being lazy. So what I want you to be able to do today is, if it's a simple antiderivative, be able to integrate it and evaluate it, because there's nothing complicated about the process. We got to get good at that first, because next week we're going to do the more complicated stuff, which is the stuff involving substitution. Right, so I will